Alrighty, indeed. I am Cody Willard, one of the volunteers here for the SKTLs, space debris crypto cleaning, space debris cryptocurrency, space debris cleaning cryptocurrency. Glad I practiced this before I got started this today. At any rate, so is Dan Geraci, who is a good friend of mine has become a very good friend of mine over the last year. And is also the chairman of the Planetary Society. But today he is here to talk about his job as CEO of FreeFall Aerospace. I guess he's going to talk about FreeFall Aerospace. Yeah. He's the CEO.
It's show and tell. That's what it is.
It is show and tell with Dan Geraci, CEO of FreeFall Aerospace. Thanks, Cabana. There's Cabana, Sanatsi, and American Badass himself. It's a great moniker. Dan, yes. It's a pleasure and honor for you to be here, and please tell us everything about FreeFall Aerospace, and I'm sure there will be a few questions at the end. People watching on YouTube could comment. Here we go.
Thank you. I think since this is show and tell, and I am not gonna, do the slides of my summer vacation or anything horrific like that, but what I'll talk about today is really the business that FreeFall is in as it pertains to what's going on around us that we talk about every week, and so much of what's happening today that we talk about, all of what's going on in space, all of these programs, all of these contracts, tens of thousands of satellites going up. What's new with Starlink? All of this. Keep in mind, it's a basic, simple fact with the telecommunications industry, but that at both ends of every single communication, every message, every transaction, every signal, everything, there's an antenna at both ends of that transaction. And antennas have evolved dramatically over the years. And FreeFall designs antennas, but they're very disruptive antennas. They're not traditional antennas. And I'll put up something for you to look at. I didn't want to put up a bunch of slides because I don't want to cross any lines on what I'm putting out there and who has or hasn't seen it before. So what I will put up in a minute is something that's public facing. But the antennas you're all familiar with, that most people are all familiar with, are those dishes, those parabolic dishes that we see, whether it's a little one on someone's roof for many years, or it's those giant farms full of them, these antenna farms outside of different types of companies. But we've seen them everywhere. And then there's the flat panels. And most people know those as Starlink. But these flat panel arrays are electronically powered antennas that, yes, they're flat, and inside that surface that might be this big could be hundreds or thousands of what are called patch antennas. Just think of postage stamp sized antennas. And they can do all kinds of cool stuff, but as you can imagine, they use a ton of power. So everything has its limitations. Those are the two types of antennas right now that have been in use for ages. Today, something has changed because of the thousands of satellites, because of the thousands of other devices on the Earth, as well as in orbit, as well as now going to the moon, that are going to be in place around the moon, and going further out as we plan for Mars. The demand is for literally millions, not an exaggeration, more antennas to service all of these different initiatives. But what has to be different is they have to be, for the Earth ones, much cheaper, much lower maintenance, and they have to be able to be used anywhere on the planet. So power has to be at a minimum. In space, what's required is they can't weigh a lot. They have to have low mass. They have to take up very little room on a spacecraft, the stowed volume, as it's called. And again, power is at a premium. So all these old antennas weren't built for this. They're big, they're expensive, and they're anything but easy to maintain or lightweight. And that's where FreeFall comes in. We decided to use a different geometry to design our antennas. So it's not that parabolic flattened dish shape, but it's rather spherical. And so when you think of spherical, obviously you're thinking of, you know, a globe like the Earth. But for the sake of our discussion, think of just half of it. So we're going to cut it in half. So, you know, what you're going to see is going to look a little bit more like a punch bowl. But the point behind this is spherical antennas allow for a tremendous number of advantages. And they have a couple of disadvantages. But the advantages far outweigh the disadvantages. And that's why FreeFall is where it is today in the process of emerging to face off against this market. Let me share something with you here that will give us something that we can give you an idea what the heck I'm talking about. Okay, I guess you can see this since it says I'm sharing it. So what this is an overview of what our antennas look like. And it's easier to tell you with a picture than it is doing the old, you know, imagine, if you will. So this one obviously makes it easier to get because this was the original idea, an inflatable antenna, something that could be utilized that's super lightweight now. Think about, you know, a heavy balloon, if you will. And this one is basically a 1 meter that you're looking at, so just a few feet across, but it can be packed in a little CubeSat, a little 1.5U CubeSat, which is ridiculous to be able to put a meter or a meter and a half, or even up to almost a 2 meter antenna in that small a space. So that gets all the spacecraft people all, you know, giggly and excited because they can put something that ends up being that big and that important in such a small space. So this was the first thing that was developed. Many of our patents, well, all of our patents have to do with spherical antennas. So this is a very specific capability, very specific technology that we control with this. Each of these, even this one, this is still a spherical curvature to this. That might look like a parabolic antenna, but it's not. That's a spherical curve. This one's obvious. That's the punch bowl. And this one is a spherical curvature. These up here obviously are for space. And our systems can be deployed from very small containers or stowed volumes in this case. This is, you know, like a 6U CubeSat, but this could be a much bigger antenna. You know, once it's deployed with this very cool origami style, you know, stand-up frame that, you know, it's like most beach chairs or other things we've all had to deal with, but this one actually works. So this is a very simple mechanism where the antenna would deploy from the bottom and pop up here. And then the feed system, the part that does the tracking, transmitting, and receiving, this deploys from here separately. Most of the time you'll see them attached to each other, but this gives us more flexibility, makes it easier to stow, and as a result allows us to use far less far less power. One of the advantages that you get with spherical, with our design, is the fact that it's a stationary antenna, or reflector, as the surface of the antenna is known, the reflector. It's stationary. Those big dishes were used to swing back and forth all the time. And we see them going across the sky as they track a satellite from one horizon to the other, and then they have to spin back really fast to catch the next one. In the telecommunications world, that's called break before make, which means the signal breaks when that antenna is swinging back before it makes or reconnects again with that next satellite rising. If you want to have continuous connectivity, therefore, you need two of those antennas as close to each other as possible, which isn't all that close given their size and their need to move, in order to be continuous. So while one's tracking one across the sky, the other one's waiting for another one. That's what most companies use. It's expensive, having to put two antennas in place just to keep connectivity at every location. You have to have antennas. With ours, we resolved that issue for one customer, and you can see it down here on the bottom left, where we have two of these feeds, these little arms, in one antenna. And so because this doesn't move, the feed just catches one satellite when it rises, tracks it across the sky, and while it's doing that, the other feed comes over here and waits for the next satellite. It's pretty logical, makes a lot of sense. It's a real tricky engineering and design and manufacturing process, which of course is patented, thank God. But this allows us to do make before break with one antenna. So this can do the job of two of the others at a much lower cost. And that story carries through all of the different executions of this same core technology of steering around the inside of a spherical surface. And so this antenna here, which is also shown in this image on the bottom here, this low profile, this is made to be recessed. This can be a few feet. This can be 10 feet across. We've modeled it even larger. But this can be used to track any kind of satellite. It can track a satellite in geostationary orbit, the furthest out. It can track them the closest to the Earth in low Earth orbit, or LEO. And so the flexibility is there. But again, there's no big motors under here. There's no big infrastructure. There isn't any on any of these designs, because the only thing moving is this little arm, that little feed arm that we were talking about over here. Those are the only things that move. We're not swinging a big antenna. We're just swinging these two little arms. And the power required for that is a fraction. For example, this antenna in the lower left, which is designed for connecting the digital divide, this will operate on most likely less than 90 watts of power. And the company's requirement is it couldn't be more than 250, because that's what they're used to seeing, is 300, 250, 750 for some antennas. This is one of our little, talk about secret sauce. That's one of our key points, is our very low power consumption. So, which brings low price. But at the end of the day, when you look at where the desire is, big ground stations, smaller ones that'll be mounted on radio towers, or could be mounted on rooftops. This is about 6 feet across by 3 feet high in size. We have the inflatables and these mesh antennas. One thing I will say is that this is a game changer, because we can point this signal down to the moon and then turn this beam with the right configuration. This isn't accurate in this image. We can point back to the Earth and talk to the Earth. Now, that might not seem like a big trick, but with today's antennas and satellites, in order to talk from the moon to orbit to the Earth and back, you have to move your satellite, because the Earth and the moon aren't lined up in a nice, simple way that allows you to just point and shoot, turn around and point and shoot. You have to change the orientation of the satellite using your attitude control system, the ACS. And those are the little thrusters that fire to reorient the spacecraft. That has to be done every time there are transmissions between the moon or lunar orbit and Earth. With our technology and our steering ability with a sphere, we can speak to both without ever having to move that satellite. That's a massive savings in fuel. It's a massive savings in other costs for those satellite operators. So again, how do we make things more efficient for a new environment where things are going to be far different than they have for the last 50 or 70 years? It requires new solutions. And so that's where we are, is trying to get out front. And the big satellite communications companies, they're all talking to us. Some of our competitors are talking to us because they see how we can add a capability. Most of the competition has no incentive to compete. The patents keep them from competing exactly with spherical in any way, shape, or form close to what we've done. And B, for them to introduce a low-cost alternative to their own products would be silly. It's financial suicide. You know, if Cody were looking at a company to buy and their CEO said, yeah, we're introducing a new product line that's going to completely undermine our entire other product line by cutting prices in half, you know, that would kind of change the calculus on the stock price performance and the earnings performance of that company. So they're not about to do that anytime soon, and that's just fine with us. But I'll stop there, and if there's any questions, great. It's I can't see anybody, so I'm talking to a blank screen here. Who's there?
Everybody.
Unmute thyself. There we go.
Yeah, there you go.
Anybody home? Oh, there you are. Okay.
There we go. I've unmuted. Dan, fascinating. So, can you just talk a little bit more about the lunar part of it and timing that you expect any of that stuff to, you know, be in service?
You know, same conversation we always have about timing. I mean, lunar, you know, NASA's going to do what it's doing, and SpaceX will do what it's doing. I think lunar for us, from a communication standpoint, is happening now. And networks are already being developed, and assets will be getting launched, satellites, to be put in place in lunar orbit, as we already have some, to start building out these networks. So just as we talk about the satellite company of the day, who's got just launched thousands of satellites, whoever it might be, whatever company, new company, we're going to have that same thing happening in lunar orbit. You're going to have multiples of constellations in lunar orbit, and that's going to really dramatically accelerate the demand for infrastructure companies first. So you got to go lay in the piping and the plumbing and everything else. And that's where we're going to see action early on is, gee, what kind of antennas are required? What kind of work is going to get done? How much transmission capacity is required? How big is the Wi-Fi network going to be, or the networks going to be around the moon? Those are all going to be critically important problems to solve long before somebody's pitching a tent and doing experiments. So I think infrastructure, obviously, for a lot of obvious reasons, will lead the way on opening up that market. You know, power, all those things. Power and communications. Those are going to be the two basics, and then survivability will go with the people.
I have another question, if I could, on the same topic while we're here. How did, when we landed on the moon in '69, how was that television signal broadcast without the infrastructure in place?
Oh, there was some infrastructure. There were a couple of satellites up that were being used to communicate. We had all the big Earth ground stations that were being used as part of the network. So our communications network for being on the moon had been built while the program got started, in the early 60s. So those ground stations and, putting them up in Australia and in other places, that came hand in hand with the satellite revolution that followed in the early 60s on Sputnik and everything else. So that was part of the government infrastructure, the military infrastructure, the telecommunications infrastructure. But for going to the moon, we needed stuff a bit further out. And so, you'll remember going to the moon, and then when they'd go around to the far side, we'd lose communications until they came back around the other side. And I can remember on Apollo 11, or even Apollo 8, actually, everybody was kind of, oh, wow, what's going to happen? I mean, seriously. But it was just, they went around the backside. There was no communication. There was no satellite on the backside of the moon that we could use for communication. We had nothing back there. So it was almost line of sight, basically. We had antennas pointed at the moon from Earth. Their antennas were pointed at that big blue marble in the sky. But now, relay satellites are going to be the thing in the next umpteen years, because it's going to be all about getting data. If you look at the Earth and then you look at space in concentric circles, like it's stacked in distance, okay, that further away you get from the Earth as you keep going out into space, everything from Earth, between Earth and everywhere else, is going to be a relay. Because we have to understand that for the foreseeable long-term future, everything we do in space, every bit of data we generate or anything we do, will in some way, shape, or form at some point come back down to Earth. Because, we're not moving headquarters anytime soon for the human race. So the bandwidth, how much processing will be done off the planet, how much will be done in other places where it might be more secure to do it. Is there a more secure environment offered up now as we move out? Some think so. But it's exponential growth. It's kind of like its own environment. Space is like that, right? How far can you go? That's what the space economy will be for a bazillion generations, unless we screw it up for ourselves.
Other questions?
Dan, who have you guys used to get your stuff up to this point? Can you say?
Well, we haven't had anything launched per se. We have one waiting for a launch on what we now find out is a less than, no pun intended, stellar performance by Firefly. It was a NASA launch. It's been waiting for over a year. Now we're finding out that Firefly's got problems with that rocket. So that may be the reason why this thing isn't going up. And if it goes up, it'll go to a very different orbit, and no one's going to get their stuff done. So we haven't been able to launch. Most of our stuff, obviously the ground stuff doesn't need to. We do all the testing here. We use the Fort Huachuca testing range in southern Arizona. They have a great RF testing range. And then all of our other tests can be done in different kinds of chambers and testing equipment. But for space, we're talking about flying with a few different people that want to test our stuff just to see how it performs in that environment for them. There's nothing in the physics that tells us that it shouldn't, but that said, until you're in the environment, you have no idea what could go wrong. So.
My other question would be then, you talked about satellites and things around the moon. What's the plan for that? Do they need hundreds or thousands of satellites around the moon, since there's nobody up there to necessarily need to transmit to, or will they put fact-finding photography type things up there to kind of map everything, so you'll still need a bunch of them? Is that?
Yeah, I think you hit it right there. I think it's think of the Earth observation market that's exploding right now, with everybody wanting to, get a pixel down to a couple of centimeters for every single centimeter of the planet. I mean, it's insane. Well, that's going to happen on the moon before anybody pretty much gets there. That's happening already, but the amount of observation assets in orbit around the moon, telecommunication, how much can you put in orbit around the moon before your adversaries find out or notice or catch up? Lunar orbit's a little trickier than Earth orbit, only because it's a much smaller neighborhood, so you don't have the vastness of Earth's orbital area to play hide and seek. Now you're in a smaller diameter neighborhood, so that'll be interesting.
Dan, would we be able to see any
South
of those?
Pole is going to be the primary target, so I expect polar orbits to be jammed with assets. What's that?
Will eventually we be able to see satellite, looking through our telescopes, looking at the moon? Will we be able to see debris / satellites in moon debris?
In lunar orbit, if they're big enough, it would be likely, only because of the high reflectivity they would have in this close. They'd reflect the way the moon does on a full moon, because that sunlight would be bouncing off pretty good. But they would have to be pretty big, and you would likely best see them on anything. Let's say you got a crescent moon and a nice dark night. You might be able to see something crossing the darkened face part of the moon. You might be able to see something, but you really have to be knowing what you're looking for. Matter of fact, the Japanese lunar rover, or the Japanese lander rather, that landed upside down, that started talking again, right? Because they couldn't find it. The imaging, was that on the moon or is that Mars now? I got myself screwed up. No, that's the moon.
The Japanese landed the upside down thing on the moon.
Arizona State imaging team found it from orbit.
Wow.
They found it on the surface from orbit.
Wow. With
links today now. Anyway, I have a hard stop in a minute, but happy to take another one.
Dan, thank you for being here. Any quick questions before we go? That was a pleasure, Dan. Thank you.
Oh, thank you. Take care.
We'll see you all soon. Next week, same time.
Thank you.
Cool stuff.
He just pieced out. All right.
He had to go.
4:30 on the dot.
He had to go. All right. Well, thank you guys. Appreciate everybody being here. And that was, fun to see what Dan's up to and that kind of detail.
Thank you.
Thanks, guys. Bye.
See ya.